Hello students, welcome to the course Verilog HDL. In the previous video, we discussed the what is meant by an expressions, operands and operators. So just we have defined. So in this video, we try to elaborate on the concept of operator types. Okay, so that is the basis of this unit data flow modeling. Okay, Verilog provides many different operator types. Okay, the operators are can be arithmetic operators, they can be logical operators, relational operators, equality operators, bitwise operators, reduction operators, shift operators, concatenation operators, or conditional operators. Okay, so some of these operators are similar to the operators used in the C programming language. Okay, so each operator type is denoted by a symbol. Okay, so that is what you need to understand from this unit. Okay, because if you have to write a data flow modeling, so you need to convert the boolean expression into a Verilog expression. For that, so you require the symbol. Okay, for which operators you will use which symbol, that is the essential. Okay, so in this today's video we'll try to cover up arithmetic, logical, relational and equality operators. So these are very simple, we have gone through in C programming also. So we'll go through this with respect to Verilog HDL, and remaining we'll take up in the next video. Okay, so first type of operators are arithmetic operators. Okay, so there are two types of arithmetic operators again. So they are called as binary operators and unary operators. So what is meant by binary? The name itself says bi means two. So it requires two operands and in between there is an operator. So such kind of operator we call binary operators, and there are unary operators. Okay, so they operates on a single operand. Okay, so these type of operator you have learned in C programming also. So now we are elaborating with respect to Verilog HDL. Okay, so first we'll take up the arithmetic binary operators and their examples. Okay, so as I told you, binary operators takes two operands. Okay, so binary arithmetic operators are multiply. Okay, so some of these symbols are same as what you have used in C programming. So multiply star will be used, divide this line will be used, lining line, then add, addition plus, subtract minus. This may not change in any programming language. Power, okay, 2 to the power 10 if you have to write, so then you have to use a double star. Single star means multiplying, double star continuously means it is an power. And then modulus. Okay, so when you do the division of two numbers, so its divisor will be the result of this divide operation, and if you put the remainder, okay, modulus, so then remainder will be stored. Okay, so that is what about this binary arithmetic operators. So how to use this? Okay, so with examples we'll try to understand. So we have three numbers are given here, a, b, d, e, f. Okay, so a is of 4-bit 0011, that means in decimal it is 3. B is 4-bit 0100, that means in decimal it is 4. Okay, so A and B are register vectors. Then along with that, D is 6, that means decimal 6. E is 4 and F is 2. Okay, so this also we have initialized. So now we will try to do the operations. Okay, so first one is multiply you had. So A star B. Okay, when you do multiplication, 3 into 4, what is the result? 7. So that 7 in binary if you have to keep, so what is the result? Sorry, 4 into 3 is 12. 12 in binary is 1100. So that evaluates to 4-bit 1100. Clear? So this is very simple, same as in C programming. Then D bar E. So D is 6, E is 4. So 6 divided by 4. So only the divisor will be kept, not remainder. So 4 ones are, right? So 2 is the remainder here. So that 1 will be stored. So divide D by E evaluates to 1. Okay, and in case if you have any decimal value, okay, so it is 1.2 is there, 4 5s are 1.5 will come. So this 0.5 will be truncated, truncates any fractional part. Okay, so that is what this is. Okay, so it will store only 1 as the result, 0.5 will be truncated. Okay, then A plus B. So A is 3, B is 4, 3 plus 4 is 7. So it is 0 0 0 1 1 1. Okay, that is the result. Then b minus a, b is larger number 4, a is smaller number 3, so b minus a will give you 4 minus 3 1. So 1 in binary is 0 0 0 1 in 4 bits. Okay, then you have the power here, f is equal to e double star f, that means it is e to the power f. So e is 4 here. Okay, so f is 2, so 4 to the power 2, this can be written in Verilog as like this. Okay, so what is this answer? 4 to the power 2 is 16, so this yields a result 16 here. Okay, so this is about the basic arithmetic, binary arithmetic operators. So some of them we have not discussed, so that will take up in the next slides. If any operand bit has a value x, then the result of the entire expression is x. Okay, so this seems intuitive because if an operand value is not known precisely, the result should be an unknown. Okay, so for example, okay, any one of the values unknown means the result we could not predict, right? It is a 0 or 1. So for example, we have here 1 0 1 x, and into another input we have 1 0 1 0. Okay, so here first bit is unknown. So because of that, sum will give you the value 4 bit x, because so in case if you consider here 0, so this result will be 0, then 1 1 0, this will carry on, right, with a carry, then 1. Okay, so 0 1. In case if it is 1, okay, so then this result will change, right? So 1. In case if it is here 1 also, 1 plus 1, so it will be giving a carry, right? So this carry means it will truncate, right? So whole results may come wrong. That's why in general, so if any x present in the operands, so the result will also evaluate to all x. Okay, so this is the point here in this case. So then modulus operators we have not seen. So modulus operators produce the remainder from the division of two numbers. Okay, so they operate similarly to the modulus operator in the C programming language. Okay, so as in C programming it will work. So if you write 13 percentage 3, that means what? 3 4s are 12. What is the remainder of this? 1. That will be stored. 16 by 4, it will be perfectly divided. So that's why remainder is 0. That is the result. Okay, in case if you have negative numbers, okay, so minus 7% 2. So always remember, so when you have negative number, so it will take the sign whatever is the first operand. So if it is first operand is minus, so it will take the minus sign. Then division, 2 7 by 2, how much? 2 3s are 6, and remainder is 1, so that's why minus 1. Whatever first operand will have the value, accordingly it will take the sign. So take sign of the first operand. If you reverse this 7% minus 2, if you do, so then it will give the result plus 1, because it will take the sign of the first operand. So this is plus here, right? That's why plus, and remainder is 1. So this is about the modulus operators, how they work. Okay, then unary operators, arithmetic unary operators. The operators plus and minus can also work as unary operators. Okay, how? They are used to specify the positive or negative sign of the operand. Some of the cases we need to write, right, plus 5 minus 5 in the integers. So to specify that, we'll use the same operators, right? Then in that case it is called as unary operators. Okay, so unary plus or minus operators have higher precedence than the binary plus or minus operators. So in an expression, if you have a unary plus 5 minus 5, that will be evaluated first, then binary. Okay, so at the end of the operators discussion, we'll see the operator precedence. So in an expression, if there are number of operators coming together, which is having highest priority, which is having lowest priority, right? So that is called as precedence. So that we'll see. So at present now, so unary plus and minus will have higher precedence. Okay, so minus 4 will be written like this. So here it is negative 4, only one operand. Okay, so it is a only one operand, and minus. So in C and all, you had operators like this, I plus plus. That means incrementing I to one value, or plus plus I, right? So hope you remember. So this is called as unary operators in C programming, but here it is called as the keeping the value of sign, because it is a digital circuit design. So minus is also having importance, right? Okay, so this is about the arithmetic unary operators. So we'll take the discussion further. So negative numbers are represented as 2's complement internally in Verilog. Okay, so negative numbers also represented in 2's complement, and it is advisable to use negative numbers only of the type integer or real in expressions. Okay, so designers should avoid negative numbers of the type, okay, so the size, base and number. So this format we should not use, okay, when you are using negative numbers, okay, in expressions especially, because they are converted to unsigned 2's complement numbers and hence yield unexpected results. Okay, to explain this topic, so we'll have an example. So it is advisable to use integer or real numbers, we told in first part. So minus 10 divided by 5 will evaluate to minus 2, because first operand is having minus sign. 5 2s are 10, so minus 2. But if the same thing, if you write like expression, okay, so this base number format minus d10, okay, so this is the base size number format. Okay, okay, so if you use the base format like this, so then it will consider the machine specific number, that is 32 will be the default machine word set. So this is earlier, so now at present we have 64 bit also. So then it will evaluate to 2 to the power 64 minus 10. Okay, so because the 2's complement format it will do, so then it will be going to be an incorrect and unexpected results. That's why should not use numbers of type in the expressions. Okay, fine. So next set of operators is logical operators. Okay, so this you have learned as gates in the case of earlier and or not, right? But now the same and or not, instead of gates we will be writing as there will be three different sets are there in this. Okay, so logical operators, bitwise operators and reduction operators. Okay, so all they will use this ampersand. If you have two double ampersand, that is logical. Okay, so first set, so we are learning this in this logical. And if you have two or, so this is an or operator. So if you have two or operators, so it is logical or. Okay, if it is single, it we call bitwise. We'll learn it in next video. Okay, and then logical not. So some cases it will be used negation and some cases it will be used this one. Okay, so if you use this symbol, it is logical not. Okay, so careful about the symbols. This is only the fundamental in data flow modeling. Okay, so operators and or binary operators here. Okay, they operates on the two operands, and this operator negation is a unary operator because it only works on the single operand. Okay, some other variable you have to complement it. Okay, complement of 0, complement of 1, okay, complement of any vector, then we'll be using this. Okay, so what is this logical operator? So what is their results? Okay, so use of parentheses to group logical operations is highly recommended to improve readability. So whenever we are using this, so we'll be using the brackets. Okay, so that is the parenthesis. Also the user does not have to remember the precedence of operators. Once we have put the brackets, so always brackets will have the more precedence. So you know the Bodmas rule, right? Brackets off, right? So accordingly, so if you put any operators brackets, so then it will not come under the precedence. Okay, so brackets will have the higher precedence. Fine. So now try to understand this with examples. So before we'll understand these three conditions for logical operators. So logical operators always evaluate to a 1-bit value. Okay, so it is 0, 1 or x. Okay, it may be any number, it will be there if it is ANDed, but it will be considering it as 0 or non-zero number. 0 means 0, non-zero means true value. Okay, so like that it will evaluate. Whereas in the case of bitwise, so bit by bit it will going to evaluate. If you have 4 bits, so 4 bit answer it is going to give. Okay, so hope you are understanding. So these the logical operators always evaluate to a 1-bit value, either false, true or ambiguous. Okay, if an operand is not equal to 0, it is equivalent to a logical one. That's what I told you, non-zero. Okay, if it is say 1, 2, 3, any number, then it is called as true condition or logically 1. Okay, if it is equal to 0, it is equivalent to a logical 0 or false condition. Okay, if any operand bit is x or z, it is equivalent to x. Okay, so in this case it is only three values, 0, 1 and x, and is normally treated by simulators as a false condition only. Okay, then logical operators takes variables or expressions as operands. They can also consider variables or expressions also as operands. Okay, so this is about the logical operators conditions. So we'll understand with examples. So we have two numbers here, a and b. So a is declared as 3, b is 0. So just for example sake, we have written just n equal to 3, 0. So first one, a double ampersand b, that means logical. And so what is 3 and 0? So it will not be considered like this. Okay, 3 means 0 0 1 1. So this is 0 0 0. This will not be evaluated like this. Okay, so this is for bitwise operator, but logical operators it will consider. So this is a non-zero number, so 1. So this is a zero number, so 0. So 1 and 0 is 0. This is how the logical operators will evaluate. Okay, then a or b. Okay, so again same way. So this is non-zero 1, this is 0. Okay, so 1 or 0 is 1, so that's why result is 1. So always the result is 0 1 or x, whatever may be the numbers. Okay, so then unary operators, so negation of a. So a is 3, but what you feel, so it is 0 0 1 1. So if you complement it, so you think that it is 12 1 1 0 0, right? This is in the case of bitwise negation. Okay, not in the case of logical. So here it will be considered as a true condition. 3 means non-zero, true. So true means negation is false, that's why it will evaluate to 0. Okay, so not of b. So b is a 0 number, so negation is 1. Okay, so this is how logical operators work. Okay, so with this example, hope you are clear with the logical operators. Okay, some more examples with respect to unknowns. Okay, so we have another example, a equal to 2 bit 0x and b is 2 bit 10. Okay, so a and b, so it will evaluate to x because it will consider it as x, and this it will consider it as 1. Okay, so 1 and x, so x is always considered as false condition, so that only it is going to come. Okay, see here, so this is how it will interpret x and 1. Okay, expressions. Okay, so it can be used as variables as well as expressions, I told you. So a equal to 2, b equal to 3. So that means we are checking this. So this is comes under equality operators, we'll see next. Okay, so this equality we are checking. So a we have declared, is it equal to 2? If it is true, then it is 1. B equal to 3, if it is true, it is 1. So then 1 and 1 will give 1. If this is 4 combinations will come, this is 0, this is 1 0, this is 1, this is 0 0, this is 0, this is 0 0, like that. Okay, so evaluates to 1 if both a equal to 2 and b equal to 3 are true. Okay, otherwise 0 will come in all other cases, like 0 0 0 1 1 0 case, it will give you 0 result. Okay, so hope it is clear how we use in the. So more we'll understand if we do more programming part of this data flow modeling. Okay, so next set of operators we are coming with relational operators. So we have seen arithmetic basic and then logical operators. Okay, now relational, with respect to relation. So like greater than. Okay, so less than, greater than or equal to, less than or equal to, so these comes under the relational operators, and these are the symbols. Okay, everywhere you should note down the symbols carefully. Okay, so what symbols we are using, and these symbols will vary from Verilog to VHDL, another programming. Okay, but hopefully you have completely studying Verilog programming only, so no need to confuse here. Okay, so if relational operators are used in an expression, the expression returns a logical value of 1 if the expression is true and 0 if the expression is false. Same as logical operators, it will evaluate. Okay, so if this condition greater than is true, so then it will give 1. If it is not true, it will give 0. Okay, if there are any unknown or z bits in the operands, the expression takes a value x. Okay, so these operators function exactly as the corresponding operators in the C programming language. Even in C programming, we have the same symbols. Okay, we'll try to explain with examples. So A I have taken 4 and B equal to 3. Okay, so both are true values. So now we are checking the relational operators. A less than or equal to B. So 4 is less than or equal to 3. So 4 is greater than, right? So that's why it is false. So false means logical 0 will be evaluated. A greater than V, 4 is greater than 3. Yes, true. That's my logical one. So then we have taken another here, x equal to 4 bit 1010 and y equal to 4 bit 1101 and z equal to 4 bit 1xx. So x part we have considered here. So now we are considering y is greater than or equal to x. So 1101 means what? It is a 13, right? So 1010 means 10. So 13 is greater than 10 or equal to. So one of the thing is true, right? It is greater than 10 but not equal to 10. But still one of this is true. That's why it will evaluate to logical one. So y less than z. Okay, so y is 13, z is unknown, right? So if any of the operands considers x, so then result will evaluate to an x. That is what the condition. Okay, so this is the example of relational operators. Okay, so hope it is clear. So then last set of operators in today's video we will see, that is equality operators. Okay, so as I mentioned previously, right? So this is the logical equality operators. Okay, so this is logical equality, this is logical inequality, then case equality and case inequality. Okay, so we'll try to understand this difference between this equal to and this equal to, and this not equal to and this not equal to. This is very important here. Okay, so when used in an expression, equality operators return logical value 1 if true and 0 if false. Same as logical and relational operators, this also will evaluate in terms of true or false. Okay, either 1 or 0. These operators compare the two operands bit by bit with 0 filling if the operands are of unequal length. Okay, sorry for the inconvenience. So that is the 0 filling of the R of bit by bit and 0 filling if the operands are of unequal length. Okay, so then finally it will be evaluated logical true or false. Okay, just we'll try to understand with examples. So this is the normal results. Okay, so table wise it is shown. So a equal to b. Okay, the first one, result unknown if x or z in a or b. So it will do here bit by bit, not like previous, and possible values will be 0 1 or x in this case. Okay, so here a not equal to b, a not equal to b, result unknown if x or z in a or b. Okay, so this is also 0 1 x. So now what is the difference between this equal to and this equal to? That is what the difference here. See, this is also equal to b, but including x and z also it will compare. If in this a, if second bit is x, here also second bit is x, even the x also will be compared here in the case of three equal operators. So that's why its result is either 0 or 1. There is no x here because x and z also it will compare. Whereas in this case, so it will not compare. If it is x is present, so it will give the result an x. Similarly, a not double equal to b. This operator also including x and z also it will compare. Okay, and it will give the result 0 or 1. Okay, so to clear this, so we will look at the examples. The logical equality operators will yield an x if either operand has x or z in its bits. So this is a question they can ask. What is the difference between this and this? Okay, so you should know. However, the case equality operators, okay, compare both operands bit by bit and compare all bits including x and z. So here it will not include x and z. That is the difference. The result is 1 if the operands match exactly including x and z bits. The result is 0 if the operands do not match exactly. Okay, so case equality operators never result in an unknown value. That is what the speciality in case equality operators. Clear? So this is the example. So we have first set of example, a equal to 4, b equal to 3. Just a minute. A equal to 4, b equal to 3, and then x equal to 4 bit 1010 and y equal to 4 bit 1101. So this is a 13 and this 10, and z equal to 4 bit 1 xxz, m equal to 4 bit 1 xxz, and n equal to 4 bit 1 xxx. Okay, so these are the various values we have taken. Now we'll use this in operators. A equal to B. So 4 is equal to B. No, right? So it is a false, so results in logical 0. So it is bit by bit comparison it will do now. Okay, so 4 means what? 0 1 0 0, and this is 0 0 1 1. Okay, so it will do bit by bit comparison. So this is not equal 0, 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 and finally it will evaluate to a logical 0. Okay, then x not equal to y. Okay, so 1 0 1 0 1 1 0 1, true, right? So they are not equal, so that's why it will results in logical 1. X equal to z. Okay, so x is 1010, and here unknown values are there. So since it is only two equality operator, logical equality, so it results in an x. Okay, now we will consider the three equal case equality operators. Z equal to, so z is 1 xxz and m is also 1 xxz. So when you do bit by bit comparison, even and x and z are also matching, that's why result is logical 1, including x or z, all bits will match. Okay, then z is equal to n. So z is 1 bit xxz, n is 1 xxx. So here fourth bit is not matching, so z is there, here x is there. Even this is a case equality, that's why it will compare each bit, so that's why it will result in 0. Okay, because the least significant bit does not match. Okay, then m not equal to n. So it is 1 xxz and it is 1 xxx. So there is a difference, right? Z and x, so that's why it is true, logical 1. So it is not equal, that's why it is true, logical 1. Okay, so this is about the case equality operators. So what we have seen, the operator types, arithmetic operators we have seen, binary and unary. Then we have seen logical operators, three operators we have seen, and, or, and negation. Then we have seen the relational operators, greater than, less than, greater than or equal to, less than or equal to. And then we have seen the equality operators. Okay, so there are more operators are there, so that we will try to cover in the next video. Okay.